Okay, it's just on 3 o'clock. If any of you are not sleeping out there, could someone just type some chat and acknowledge that I'm audible and possibly visible as well? Okay, thank you. Thank you for acknowledging that. Otherwise, I feel like I'm a little pixie here on my own. So I'm recording this, and I'll probably post this up on the Moodle site when it's all done for what it's worth. I'm going to share my screen and basically have a bit of a rundown on what I think is going to happen. So this is where we are. We managed to get to semester 2. And today is week 4. For some reason, I don't understand why week 4, but it is week 4. And we've got this week we've got just this lecture class, but next week we've got labs. I'm going to talk in week 5. We've got image exercise 1, which I've delightfully called AP versus PA. That's going to be a kind of a paper-based exercise before we do some spreadsheet stuff. And I can talk maybe a little bit about how that's going to run next week. I believe you've been divided into groups of 16, 17 each. And so my intention is to Zoom a link to each of you before your session. And then I'll be there while you're going through this to help you do it. And if you have questions, the idea is that we just talk about it and get things right. And at the end of the session, we'll organise how to write a report and how it's going to be assessed and so on. So if you've got questions about the exercises, we'll hang off until we get to the end of today. If you look down the list of weeks, which ends in a revision class and an exam, then the week following the exercise, the first exercise, we're going to do some lectures which are important. So if you're thinking about which weeks are really important, week 6 is pretty important because it's going to talk about how to modify images. Week 7 is kind of interesting, but for me, it's kind of like a third of imaging that you'll get to use when you're more experienced. And week 8 is ultra important because week 8 is on Fourier. And for those of you doing third year CT and MRI in particular, week 8 is kind of like, whoa, I need to know what Fourier transforms are and at least understand them for next year. Then there's some stuff in week 9 on pressure and flow. And the reason for putting that there is to talk in conjunction with what you've learnt about radiography, about angiography, is to basically talk about why does blood flow, how to get it to flow, what makes it flow faster, slower, and so on. And then in week 10, I'm going to talk a little bit about the human vision system. That's my way of linking back to the things that we've been doing, like filtering images. How does your eye and brain do the kind of things that we can do on our computers? And in week 11, there's kind of a lab session, but I'm thinking of shortening it because it's right on top of the revision class and practice exam, that I'd get a little, maybe people to write a little group essay or something on skeletonization, which is like, how do I deal with 2D and 3D shapes in terms of measurement? And to me, that's an interesting part of the problem that we got to tackle in this course. So the whole idea of the course is, how do I process images? How do I regularize them? How do I analyze them? And more importantly, how do I preserve the information in them and get the information that's in the pictures out into the real world? It's getting the information out that's important to you, not just taking the pictures. So today we're going to talk about some key concepts, and also this is a sort of a preliminary to the lab work that we're going to be doing next work. So a lot of this is going to be kind of revision-ish, talking about the DSA and stenosis and blood vessels and measuring them, because it's a nice case study in how to do imaging is to do arterial imaging, because there you're kind of at the limit of not just taking happy snaps, but taking images which are quite hard to get in terms of signal to noise and spatial definition. So that's the kind of reason for having this unit conjoined with the image processing physics part. So I'm hoping that it won't be too rushed today and that we can kind of just wander through. I am encouraging people, if they want to interrupt or pause things, that you just click your mic on and say, Immens, you completely lost me, or Immens, I've gone to sleep, could you go back and repeat that? Otherwise, it's a lonely seance here by myself, just talking about these slides, which I know very well. So we're going to talk about digital discretization. This topic here, discretization, is something that a lot of people kind of just assume happens naturally, that somehow you can just take your camera, your phone, take a snap of something, and that doesn't really matter if the pixels are all kind of just little blocks. Because in the real world, we don't have a real world built of Lego bricks. The real world is semi-continuous. And we will see later that how you cut images into rows and columns can make a big difference. Is that a question or just a joining? Possibly just a joining. Okay, so we're going to rocket on and talk about this. This is the kind of overview of where we're going to be. I'm not going to talk about DSA in particular very much. Before we do talk about this, I'm tempted to go back and do what I promised, and that is go back to this. So we saw these slides in semester 1 in 2012. And so I'm not going to go through all of these again, but I'm hoping that you say, oh yeah, I remember Immens talking about this, but I don't remember what it means, but I do remember seeing these slides before. So I'm going to kind of quickly go through these as a preliminary to doing the lecture material, which I've just started on. So if you're thinking, why is Immens leaving lecture 1 and 2, I'm going to come back, and I'm not going to do all of these slides, so don't panic about this is going to be very, very, very boring if I know it all. So we talked about X-ray production, and that was, I'm kind of assuming that now we're all on the same page and we know exactly why this point here, the cutoff point, and why the mean energy here is so important in terms of X-ray image production. But that's the mechanics of image production, which is really adjunct to the problem of making and acquiring images. And yes, we know how electrons lose their energy and the importance of Bremsstrahlung, yes, and we know about our enemy, Mr. Compton, who conspires to try and produce scatter in our image that makes them less sharp than they could be, so we don't need to talk about that. We will talk about this because this is attenuation coefficient for soft tissue. Next week, we're going to do an exercise where we look at this graph, and I've put an arrow here, which isn't in the original slides, but that's at 10, 20, 30, 40, 50. It's somewhere between 50 and 60 keV. And you know why I put this here, I think, because traditional X-ray radiography on people would run with kVp at about 120 or 150 kVp, certainly not 200. And so where this arrow is, well, tissue is somewhere around here. It's about 0.2, and the units are centimetre squared per gram. And if the centimetre squared per gram has you worried, you'll remember that the density of water or soft tissue is about 1 gram per centimetre cubed. So you can convert this into centimetres to the -1 per centimetre by just multiplying by 1, which is easy. So 0.22 is roughly the absorption power for X-rays of about mean energy 50 to 60 keV. And we're going to come back and use that next week as an exercise to say, let's track X-rays through soft tissue and see where they go and how many end up at different parts in the body. So we know about the difference between carbon and copper as Z increases. And we know about the K edge in things like iodine and barium, which is why we're using them as contrast media additives for angiography enhancement in particular. So the top two values are interesting because these guys are used for contrast medium. These guys are interesting because these are the peaks that you see in the X-ray spectra. And that's probably why it's a good idea that we have a mean energy of around 60 keV, because that's aided by the presence of the K-shell emission peak, which happened to line up in about that point when you were using tungsten for an anode material. So I'm going to skip along. Some more graphs. Remember the K edge and the L edge and the M edge. Yeah, that's all going to happen. Remember X-rays being attenuated by the body. This is low KV. Notice the top line here, it says 30 KV. So that would be, I would be thinking this is like, oh, he's doing hands or wrists or something, because that's a relatively low energy. And so we looked at this slide and we thought, I wonder how many ODs I can get, what range of image contrast I'm going to get with that kind of KV MAS combination. And sure enough, here it says that 0.5 centimetre of bone and tissue, we looked at the relative absorption of soft tissue. So this is 3 centimetres of tissue is producing about 37% transmission of, attenuation of X-rays. So 63% absorption. We'll come back to this in the lab. And then if you change the energy, was 30, on next slide it's 60, then we see that because the KVPs have gone up, and here we are at about 0.22, so you see the numbers here, then we're in the regime now where we're getting a smaller range of contrast because the X-rays are more penetrating, and so we've got 3 ODs of image contrast. The numbers along the bottom here, these are powers of 10, so this is 1,000 times brighter than the middle. This is 100 times brighter in the middle. This is 10 times brighter in the middle. So as you go from full absorption through the full thickness of the patient to just the air, this is I0 out here, there's a factor of 1,000 between the darkest part of your image and the edge of your subject. And we'll talk about the dynamic range, what effect that has in the image later today. In other words, the range of brightnesses that you'll see in an image, and how important is that relative to, for example, the number of pixels that you have in the image itself. Yeah, we talked about making X-rays. The diagram, I'm smiling because this is to reinforce our picture that X-rays unhelpfully go in all directions rather than just down through our LBD, and we remember all that. So we talked about how many X-rays you need, and we talked about dose, noise. And so this is the slide 16 is the one that I wanted to jump to, that says when we have a uniform beam, so forget 1.5 squared variation, forget anode heel effect differences in the intensity distribution coming from the X-ray anode, imagine you had a parallel beam, so no angular divergence, but with uniform intensity, and you shone it through uniform tissue, then you should see an image IXY where the absorption through the same tissue everywhere should produce the same level of grey. And so the histogram of this image, perfect parallel beam, uniform monochromatic X-rays, should produce uniform absorption in a uniform object. And so we should have this peak that says in this image, a patient thickness of say 10 centimetres should produce exactly the same absorption. But we know that even if you had a perfect monochromatic, no divergence beam of 60 kV, that you will see this kind of image where we're expecting to see quantum mottle. And the quantum mottle is a reflection of the fact that the absorption process and the X-ray production process means that I0 is never exactly constant everywhere, nor is the absorption constant everywhere, even if the patient is uniformly thick. And why am I sprouting on about this? It's because when we define uniform, we really mean something like this, that says there is a mean absorption, I, which is well characterizing the tissue that we're looking at, but there's also this variance that says there is a range of intensities that corresponds to this X-ray absorption, and that range of intensities is dominated by the absorption of the patient and the X-ray production process as well. And you might think, well, Emmons is getting old and pernickety and getting too concerned about little things. But then when you switch to the next slide says, yes, but if you have two different thicknesses of tissue or two different types of tissue, liver versus fat, muscle, then the absorption won't be the same, and I'll have two different transmitted intensities, even if the objects were the same thickness, but I'd now expect two different intensities. And so when I translate from the imaginary perfect world of X-rays to the real world of X-rays, I have this motley picture from I1 and another motley picture for I2. And when I look at the distribution of grey levels that those image produces, there is a mean for I2 and there is a mean for I1, but I can only tell that these two materials are different if there is some contrast. In other words, if this doesn't go down at all, in other words, if there's no minimum here, I can't tell that there is a difference between this tissue and this tissue. And in first semester, we talked a lot about contrast resolution. And for those of you who are still struggling with this concept, and some of you still are, this graph should, in your mind, say this is what we mean by contrast resolution. It's, can I tell that this grey is statistically, deliberately different than this one? And yes, I can if this minimum is low compared to these maxima. We can define a contrast ratio based on these maxima versus the minimum value between them. Obviously, if this minimum goes to 0, then we've got perfect recognition between tissue type 1 and tissue type 2. And if you think that doesn't matter or that this is kind of irrelevant, imagine this was cancer tissue, and on this side, this was healthy tissue, and you're a surgeon who has to draw a knife line through here. And some of this tissue here looks healthy and some of it on the other side looks cancerous. And so we have to be careful about when I draw my knife through here, exactly which tissue am I going to cut, based on the contrast of the tissue. And I don't want you to get concerned or confused with the idea of spatial resolution, because now spatial resolution says, can I actually tell that I am in this tissue as opposed to this tissue based upon the position, the location, not the mean brightness of these pixels. So these graphs to me are important because they summarize the two main things in image processing. That is, do I have contrast resolution and do I have enough spatial resolution to be able to pick out where those contrast resolutions are in fact meaningful? So we're going to talk a lot about measurements in this vein. So I'm going to skip through some of these slides because we've done them before and we talk about different distributions. I'm just going to show some pictures that you've seen before. But here is a picture on the left of what looks like quantum model. It's actually something you'll probably never see in imaging because this picture has got a uniform distribution of grey levels. In other words, the number of white pixels and the number of grey pixels is exactly the same. So if you go through this image, you will find exactly the same number of grey level 87 pixels as there are 88 pixels and 89 pixels. So this kind of distribution is kind of unusual to find in imaging because it's unusual that all pixels will have roughly the same frequency in their grayscales. But we do see this in things like Bremsstrahlung spectra, where you have equal numbers of photons roughly at increasing energies, even though as lower energies increase, this graph will go up. So we do see situations where the distribution of grayscales can be quite linear, but unusual in imaging. We talked a lot about binomial distribution. So these are histograms for different noise distributions. Obviously, noise is going to be important in this course because you people spend half your life trying to improve SNR, the signal to noise ratio. So we need to talk about noise in all its manifestations. So I'm going to skip through these because we know about binomial distributions and we know about Poisson. We know about Poisson because in X-rays, whenever you are getting close to the photon counting limit, your distribution is going to look more Poisson than binomial or Gaussian. So keep Poisson in the back of our minds because when the counts get low, this is the more likely noise distribution that we're going to have than in bright field imaging where we've got lots of photons coming down. So here is a picture, an example. Image on the left is clean. Image on the right has had Poisson noise added to it. If you look carefully at the image on the right, you can see, my mouse always keeps disappearing in zoom, you can see here that there's a lot more mottle over here than there is on the other side here. So this image has deliberately had, it's how this image would appear had you used a low MAs to take the same picture. It should look more mottled than the one on the right. So it's Gaussian. I'm not going to go through Gaussian distributions, but we're going to look at a Gaussian image. So is this image the same as the noise image I showed you before? I don't think so, because even though it looks random, you can see that there is now an average grey behind these pixels, that if you smooth these values out, there would everywhere be the same kind of mean level. So when we histogram that grayscale distribution, we see there are no white pixels here. There are none at all, but 255, and there are no pixels which are exactly black. Or if there are, there's probably 1 or 2 or 3 of them. But we do have a mean value here. In other words, there is a grey level where the most frequent grey, there are thousands of them, 4,000 pixels have grayscale 120 something. And this is the variance. This is the range of grayscales that we have about the mean. And so this is typically the image that I'm showing on the left here. This is typically what we would see for real imaging situations where we have a lot of photons, but there is still statistical absorption and production variance. And so we don't get a single spike, we get a distribution. And this is going to affect our contrast resolution when we look at data in the real world. So here is a picture, same picture, perfect picture on the right, on the left. And again, the Gaussian image here. And at some stage, you have to think, I wonder how much Gaussian noise you put in here, because clearly we can change the level of noise. This has no noise. So at some stage, someone's decided what level of noise is present here. So we should be able to measure the signal to noise ratio of the right image compared to the left. And we should be able to do that even now, I'm hoping. There are other ways of getting noise. This slide, which you're well past knowing because you're second years, you know that the best way to eliminate that kind of noise is to just increase the MAs. The electron beam gets stronger on the anode and the right image becomes more and more like the left image. But we know that that's a no-no because of ALARA. So if you have a noisy image, this is the Gaussian image, and if you wanted to reduce the amount of noise, we're going to try and find ways to process image data where we can go from this image, which is noisy, to this image, which contains visibly less noise. You can see out here that the noise in this region is very much reduced. But if you're looking at this critically, you'll also say, Emmons, I think the sharpness of your image on the right is much worse than the sharpness on the original noisy image. So we'll have to learn techniques that say, if you want to increase the signal to noise of an image by removing the noise, do we do that uniformly? In other words, here has much less spatial sharpness and definition than it does on the original. So we have to be careful when we apply these image filtering operations that we understand exactly what we're doing to different parts of the signal information. It may look smoother, but the smoothness comes at the loss of not just noise, but spatial sharpness in the patient's detail. So that's linear smoothing. Linear simply means that if you double the noise here, then the noise will be halved after you apply the filter. So it's proportional, right? If you increase the amount of noise, then the noise reduction from this filter will just be scaled in a linear fashion. In this case, the filter was a 5x5 averaging filter. We'll do some of these in about week 3. We'll be applying these. So here is a different example, the same image, and now we have something called non-linear smoothing. And if you look at this, yes, this noisy section here looks much smoother here, but the sharpness of this also looks comparable to here. So we may be able to find, in some cases, image filtering operations that enable preservation of image sharpness, but not at the expense of removing patient detail. And so this is an important aspect of imaging physics that says, if it's non-linear, can we actually have the best of both worlds? And we have to be careful here because this non-linear simply means it's going to be very hard to go backwards. If you have a linear process, you can wind it back. If it's not linear, it's very hard to undo this effect. And so any non-linear mapping comes with a high price, and that is non-reversibility. We'll see that too in the lectures that are to follow if we're still here. Here's some odd noise that you will only see when things go wrong. So in an image, when you see things like these white dots usually represent either pixels that are inactive in your, for example, a discrete digital X-ray recorder. If there are pixels which are defective, they may in fact not record intensity at all, and so they always appear permanently white. Or they may be signals that have been lost in transmission from a remote site to a centre, for example, if there's been a file interruption and some of the pixels don't get sent properly, and so they're not populated. So this is what we call salt and pepper, because the pixels can be either white or they can be black. If you look carefully, you'll see there are some black holes here. There are a lot of them. Normally, you wouldn't have this many defective pixels in a real image, but I've just peppered a lot of salt and pepper into this image to make it obvious. But there are black spots and white spots here. So this is very different noise from Gaussian noise because the noise is black and white, and you might think this is easier to remove from an image, and you're probably going to be right. Here is another form of noise which is called speckle noise. And speckle noise is kind of like salt and pepper, but it's a bit more than a point. They're kind of globs of pixels which are uniformly brighter or darker, and hence the specks. So they're not salt and pepper, they're more like, well, coarsely ground pepper and salt, cracked pepper, cracked salt. And again, if we're clever, we'll be able to tackle on how to remove these without damaging the underlying image. And here is an example. So it doesn't have the original anymore, but that salt and pepper image that I had on the previous slide, this has actually been fixed by the 3x3 median filter. And this is a speckle removal filter that's removed the globs of unground pepper and unground salt from these images. Again, tread carefully. We're not allowed in radiography to change the content of the patient's anatomy. So any of these operations that you apply, you have to be mindful that you can't lie to the conferring doctor, because you're supposed to be representing a faithful picture of the patient's anatomy, not some cleverly tricked up answer where you've removed the noise but also altered the patient's anatomy irretrievably. So yeah, we're going to talk about things like histogram equalization in a minute, that says here is an image and this is its grayscale distribution. And you can see there are lots and lots and lots of grey pixels that are similar in colour like this, some very white ones and a few dark ones. It means that these grayscales are overwhelmingly populated, and so the contrast is not uniformly spread across black to white. And we can try and change that by doing things like this. So now you can see it's the same histogram of grayscales, but now the contrast has been stretched from black through to white. When we stretch contrast, we obviously stretch in the image the spatial definition of parts of the patient's object as well. So this is like an extreme window and level operation that you would apply to your images. And clearly, again, we have to be careful about any mapping that's not linear in terms of keeping this together. So now I'm going to go back again. I'm sorry. So that's the kind of revision part of where we're up to. I'm conscious that I'm talking a lot and it's already 3:30, so I'm going to try and not talk so much. And go back to where this. So spatial contrast resolution, spatial resolution, noise, Poisson, Gaussian, speckle noise, salt and pepper noise. We're going to have to learn to deal with all those. And along the way, we're going to try and learn how you do it with your eyes and how machines might do it for us in machine vision type applications to take the load off human processes. So angiography is kind of interesting because it's the first time you've done imaging where you don't want to see the patient's anatomy. In fact, you want to suppress it. And all you want to do is see the arterial part of the patient's anatomy. And that's kind of even more challenging because the arterial part generally is veins and arteries, which are millimetre in width. And it's pretty hard to see millimetre type soft tissue structures superimposed on the strong absorption of bones, cartilage and tissue in the human body. So angiography is kind of a prize attribute of imaging which sharpens our skills considerably. We've done some of this in second year, first semester. We've talked about the need for registration. Most of you on the exam in 2051 managed to explain to me why we log map values rather than just doing image difference between contrast and non-contrast injected projection images. And the penalties that we have that are associated with these log mapping, because the log mapping, while it's very useful, is also pretty brutal. And we're going to learn about the positive and negative values because whenever we subtract, we're going to get an excess of positive and negative values. And so some of our images already have minus intensities, which is something that you wouldn't normally come across when you take happy snaps. You don't get negative values in pixels, but we will in angiography images, and we have to deal with that again as well. I'm not going to talk about the history of DSA, happily for you. Moving on. DSA has some pretty tight requirements in terms of spatial resolution and time resolution, which again, I'm not going to dwell on, but there's no point having image exposure times that are so long that the pulsatile motion will blur the artery and make it even harder to see because it's smeared across the film instead of being sharp and in the one spot. So spatial and time resolution, again, to the forefront here. So the next slide. Ding. So this is me saying, imagine you had, so the blue squares here, the blue coloured shapes, and not all squares, are meant to represent arteries seen in cross section. So I want you to use your imaginations and imagine that if you looked at that square on the left, the blood would be gushing out towards you, coming out of the page. And so why are these pictures here? I'm interested in, from an imaging perspective, of saying, I wonder if the projected image in the DSA procedure depends upon the shape and orientation of the vessel itself. And so I've drawn 4 vessels here, a very unlikely physics kind of replica vessel, which is got square cross section. And then just to be a little bit strange, what would happen if that square cross-section happened to be tilted with respect to the plane of imaging? So these arrows at the top represent X-rays, which are going to pass through these arteries on their way to a film underneath. And so here is a third artery or vein, which is more realistically circular in shape. And here is a fourth artery, which is kind of elliptical. And I'm wondering which one of these is the most realistic shape that I should worry about. And I'm thinking, well, these are a bit marginal, this is good, but this is probably the most realistic shape that I'm going to see for an artery or a vein. Why is it more likely to be elliptical than circular? Well, I'm thinking that these arteries and veins have to pass between muscle, fat, and organ tissue. And so they're most likely going to be spatially confined so that the artery has to push its way through existing organic structure. And so this is kind of a more realistic picture of what an artery and so I'm interested in what kind of projections these things would offer. So I'm going to stop sharing for a minute. And I'm going to hold up some pictures for the camera that kind of answer the first part of the question. Let's say, here are it's orange rain coming down, it's X-rays pouring down from the top of the page onto a film, which is running horizontally on the graph. And we're measuring distances D along the bottom. So X-rays I0 pouring down. There is an artery here, a square an immense artery, uniformly absorbing artery, a square of side L. And all I'm asking you to think about is, I wonder what the shape on the image plane will look like for this artery. And I'm thinking if you have a square artery, then it'll just absorb e to the minus mu L every time you have one of these little things here. These X-rays have no attenuation or no relative attenuation, because remember, we're subtracting the body in which this X-ray, this artery is in a body. And when we're doing DSA, we're subtracting the pre and post contrast. So this I0 is the I that goes through the body without factoring in the absorption of the body. We've removed the body by DSA. But the absorption increases when I put contrast in here, for example, then this looks very different to the tissue left and right. And the boring thing is that I just get a square profile. If you were an angiographer, you would like people to have square arteries, and you would like their arteries to be oriented like this, because then the arteries leave a perfectly rectangular shadow. And it's very easy to say, I wonder if this artery is stenosed or not, because it has a sharp edge on the left and a sharp edge on the right. And the difference between these edges gives me the arterial width almost precisely very easily. So in Emmons's cubic artery land, angiography becomes considerably easier, because stenosis just means I wonder if this rectangle gets wider or narrower as a function of arterial position as I go along. So that's the easy case, but the least realistic case. I've drawn the second case here, and I'm drawing these because this is going to be what we'll be doing next week in the lab. We're going to think about what will things look like when I shoot X-rays through a patient, and how will they come out the other side, and what do I make of the numbers that happen. So this is the second case on the previous slide that we had. And so now I've got the same artery, and the reason I've drawn the same artery is it's got sides L by L, so it's a square. And when I think about the difference between this artery and this artery, well, there's no difference in terms of the capacity to carry blood. So if the cross-sectional area is the same, and if the pressure from the heart is the same, then these two arteries will have the same metabolic benefit to the tissue they supply. They're both capable of producing the same transport of blood inside a patient. And yet their profiles of absorption look really different, because now the same artery, which has the same carrying capacity, but it's just tilted by 45 degrees, it now has an absorption profile that looks like this. And you might think, well, okay, what's so special about that? It's a little bit harder now for me to say, I wonder where this artery starts, because in the real world, this I0 is not flat. It's got noise on it. It's got contrast resolution limitations. And yes, there is a dive down to a minimum. And yes, I know what the minimum is. The minimum is now √2 times deeper, because the central part of this artery is now much more absorbing, because the path length through the same artery happens to be, in projection, longer. I'm wondering if you think the area under here, the area of the missing bit, and this area are the same. So, do you think these two graphs have something in common? One is wider than the other, but the other one should be deeper than the other. And we're going to think about that in the labs next week and try and quantify that. So as a third and final example, as prep for next week, we go to the case of a simple circular artery. And so now everything is the same as it was before. And now I've got the same area, because I can make this circular artery have L squared, the area of the artery, being exactly the same as pi r squared. So the absorption on this object should have the same total as the square arteries I had before. So in the lab, we're going to talk about, I wonder how I can make these arteries easier or harder to see, because I'm interested in not just are they there, but I'm interested in really their blood carrying capacity, not so much the width that they have, but their blood carrying capacity. And I want to make sure that that's independent of the shape of the artery that presents, because shape changes aren't the same as stenosis. I'm going to go back to wherever I was, which I can't remember where it is. So we're going to go on and do this in next week. So this is kind of like, okay, we've done a prelude of the lab that's coming up. So I'm just waiting to get my little, okay. Okay, we're going to talk about noise. Okay, so we're back now on this. And I'm thinking it's 3:42. So my plan for the next kind of at least half hour is to go through some fundamentals of image processing, and then also some nomenclature and jargon that we use for digital image processing, which will turn out not to be examinable, but at least we need to know it. So because I've finished doing projections through an artery and we're about to talk about imaging fundamentals, this is like the basics of image processing, I'm thinking it's a good time to stop, give you people time to put the kettle on or fire up your favorite coffee engine and have a break and come back maybe just before 4. So I'm going to put the brakes on here. If people want to ask questions, if you're still here, I'm more than happy to respond to questions, but otherwise, let's do your exercises, stretch your legs, and come back just before 4, and we'll continue. But in the meantime, I'm sitting here. If you want to ask me a question, pop on. The recording is still going, so if you want to say something and be, yes, it's being recorded. Off you go, have a cup of tea.
Thanks.
Okay, I've just resumed the recording Thizo. And so I'm going to go back to screen sharing mode again. And I'll try and remind people where we were. So we talked about this. So I'm assuming that most of you have at least got up a stretch your leg, gone, patted the cat, fed the dog, made sure that you've got plenty of food for dinner, and now you're back at your resting position. I'll try and make this as least painful as possible to get to the end here. So we're going to talk about this in groups next week, as groups in the lab section. I don't know why that text there because I'm not going to read it. Okay, so this is now slide 12 on lectures 1 and 2, which is called something else now on Moodle. I hope you've all found the lecture site and the content appropriately. So this is now, let's get down to some simple definitions. So on the left is a blue square. It's meant to represent an image with n pixels running horizontally for columns and n rows of pixels vertically. The little pink dot here is meant to represent a single pixel at some location X and Y. And at that location X, Y, we have recorded an image intensity of G. So the G belongs inside this box for that pixel. Normally, we have the values of G will range from 0, traditionally given the label dark, black, no intensity, ranging through to less than 256, which is white. We see why it's less than 256 at the end of today, because this is an 8-bit image, so there are 256 grayscales, including 0. It's a 2D image. If you want to make this a 3D image, we'll just run another axis along the Z and have pixels running in X, Y, Z to make a 3D data set. Irrespective of whether it's 1D, 2D, or 3D, from this image, an inherent property is the image on the right, the green, lime green patch of brightness here. And this is the image histogram. And it's not that hard to work out what's going on here. The horizontal axis here says, let me draw from 0, this 0, all the way through to 255, which is the maximum value of G. So the horizontal axis here is image grayscale. The vertical axis on this, so this is a two-dimensional graph, not a two-dimensional image. It's a one-dimensional graph of the two-dimensional image content. And it could be the one-dimensional graph of a 3D content if this graph was n cubed, for example. So what is this graph? The vertical axis says how many pixels had a value of G. And so for each value G, you say at this G, there were that many pixels. So where this graph is low, there are very few pixels that have these grayscales. Where this graph is tall, there are many pixels that have these grayscales. And you might think, what is the utility of this graph? We'll see that this graph is a shorthand way of interrogating information in the image. And it's a kind of a fast way to do that interrogation because we've got, say, 1,000 by 1,000 pixels here. That's 1,000,000 pixels to worry about. This graph has only got 256 boxes to worry about. So there are 256 bits of information about this 1,000,000 pixel image. So this graph is a shorthand version of, I wonder what's in my picture. And I'm going to try and tell you what's in my picture in 256 ways. So notice that the area under the graph is n squared. Why is the area under the graph n squared? Because if I count how many pixels have all possible grayscales, I must count all possible pixels, which will be n squared by n squared. So all the information in here has been summed here. Okay, so this is just a histogram. And I've drawn here a very simple histogram for a 5x5 image. And these are rows of pixels and columns of pixels, and the numbers in the boxes represent the intensity measured in an image. So this is like a 5x5 image X-ray. 0 means no photons recorded, 9 means 9 photons recorded here over the exposure interval. For that image, here is its histogram. So there are 25 pixels here. There are only 10 entries here because the grayscales range from 0 to 9. And sure enough, if you add up, 9 pixels had grayscale 0. Here they are, 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's only one that has grayscale 9. And I think I can find 1, 2, 3, 4 pixels that have grayscale 5. So the area under this graph should always be the size of my image. Okay, so there's one short and not so interesting fact, but the area under the graph sums up everything inside the image. No pixels have been marginalized in this process. And so then we look at why is this histogram useful in the next slide, and we see, okay, so let me now on this histogram say, there seemed to be a natural break here. In other words, there were lots of these pixels and then nothing happened, and then there was this little group of population and then nothing happened, and then there was this. So let's put an arrow in here and say, show me the image that corresponded to pixels less than 2. And so that's this image here, because all these pixels and only these pixels have the grayscales with less than or equal to 2. So that's interesting because those low intensity images might correspond to what we call the background on the image because they're peripheral to the central content. Now, the value 0 doesn't mean that it has to be low X-ray flux because this could be an attenuation image. So there could be no attenuation. So this could be air in an image where there's no attenuation. So this then represents background. So why is Emmons getting excited by this? Because instead of looking at this image, which has got potentially 1 million pixels in it, I'm looking at a histogram which has got 256 grayscales, or 10 here. And by putting a little arrow here, I can already separate the air from the patient because the air will have much larger transmission, less absorption than the patient. And so the patient is anything that's not the background. So the patients are all these things above the background level. So I'm doing segmentation, classification on a patient's image based upon this scant piece of information, which I'm calling an image histogram. And I've put another arrow in here that says there's not much happening in here. And so I wonder what the difference between these pixels are and these pixels. And there you might say, well, clearly this is bone where the absorption has been very high. And this is soft tissue where the absorption has been much more than in air, but less than bone. So I know this is a contrived example, but I've contrived it in a way to try and convince you that when we have an image histogram, the grayscales in the image naturally partition into dense, intermediate, and light absorption objects. The beauty of choosing these points here to cut between air and soft tissue is that if I made a mistake here and said, oh, should I put the arrow here or here? I'm not changing anything because all these values are a local minimum. And so if I choose to say, where is the bone in this image, setting a threshold here between 6 or 7 or 8 will not mess up my result because I'm changing as few pixels as possible by operating at a minimum in the histogram. A minimum in the histogram divides classes of objects depending on their relative intensities into groups. And I want to be able to do that. And so then if you're a radiographer and this is the histogram of Emmons's X-ray that you've just taken, then it says in blue at the side here, this is a bad image. It's a bad news image because you put some text in here. you'll notice that there are no minima in here. So there's no natural classification of background to foreground. In other words, you could make an argument that this continuum of grayscales is really the same object. It's just that some of it's thicker and thinner, but they're all the same class of material. So before you go and look at your radiographic image, which is 1 million pixels, you could look at this histogram and on the basis of a very small amount of information say, oops, I think this is a reject. This is a reject because all I can see is background in this image. And so it's as if the patient caused almost no absorption. So this is basically all air pixels. And just from this graph, I can say, well, okay, that kind of means that KVP was too high because with KVP being too high, all the X-rays went through the air and through the patient willy-nilly. And basically I can't see the patient in here because these graphs show me that this is all background object. And so then being a radiographer, you say, whoops, KVP was too high. And you take a second picture and you get this. But this is also a bad news picture. Why is this also a bad news picture? Because it's just a reversal of the previous case that says now there is absorption everywhere in my image because all the pixels are basically showing strong absorption. But again, I've got no air in my image because basically there's no reason to think that these pixels belong to anything other than the same object. So the object looks like absorbing from patient through to air with equal transmission. And so then you take a third image and it looks like this and you think, finally, I've got it right. It's neither too transmissive nor too absorptive. I've got it just right, but it says this is bad news because, and why do you think this is a bad news image? Well, because this is no better than having all background or all foreground pixels populated in the image. It basically says my image consists of the same grayscale everywhere. So there's no contrast in this image. All the pixels, whatever the patient was, or the answer is that the patient was a uniform blob of tissue, equally thick and equally dense everywhere. And this is the answer. So the conclusion I would draw from this is either bad imaging technique or your patient is featureless. So we want something like this. And there is a story behind this shape, which I won't go into, but it has to do with the French poem. And so this diagram is much more encouraging because you can look at this diagram and say, look, there are a heap of darkish pixels here. Maybe they're the ones around the edge of the patient, which is here. And there is a minimum here that says this is the dividing line, the transition between the patient pixels, soft tissue, and the background tissue being air. So I would be tempted at the minimum here to do a threshold to say the patient is brighter than this value because these are background pixels. And then when you look at the patient absorption, you think, well, there is actually a couple of different, or maybe 3 different sorts of absorption happening here. There are 2 lots of soft tissue, which are different by this contrast point. Can you see what I'm making the point? Remember the graph that said, here is the mean absorption and here is the variance. Here is the mean absorption and here is the variance of that tissue. So you could say here are 2 tissue types and this is their variance. And here is a 3rd tissue type with its variance buried in this histogram. And we could try and extract these 3 peaks to say bone, muscle, fat, background. And we can do this all on the basis of the grayscale values in an image. Grayscale values are pretty important. So here is a real image. It's a CT image of a tree trunk. We take its histogram. The histogram looks like the blue curve here. We partition them into 1, 2, 3 groups, and where these little peaks are, these little green bars, these represent the green bar here says, this is the air. outside the tree, the background, air in your X-ray image. This is the softwood, the grey bits in my image. And these little bump over the top here, these are the tight wood, the grains and the knots in the wood. And so I can now turn this histogram into a segmented image of white hardwood, softwood background. So I'm an advocate of looking at your image histogram. And someone asked me before about why do I want these image values spread across from black to white. I want the white wood to be as far as possible away from the grey softwood, as far as possible away from the background. I don't want these sitting on top of each other because they will make tissue segmentation more difficult. I want to have contrast resolution maximised by keeping their ranges spread apart as far as possible. So the next section I'm going to prattle on a bit about lookup tables. We've talked about lookup tables before, and a lookup table, if you're confused, is very simple. It's a graph that says, given some input value, and it's just ranging from black to white or 0 to 255. So here is an input value, and it says, if you have this input value, then the output value will be here, G prime. And this scale runs the same length from 0 to 255 in this direction. So pixels that have this value of G are remapped to have this value of G prime in the new image. So old image in, new image out. There's some words here about monotonic. Usually you like these graphs not to go down and up. They usually would like to be monotonic, increasing. There is a problem here, and I won't talk about that. That's confusing. Let's just keep going. About monotonicity, we can get back to this. And so here is first year flashing before your eyes again. It's the H&D curve that says, oh, on film, there is this fog level. And if I operate down here, I can't see any patient details because the input grayscales can vary, but the output grayscale stays the same. Or I can have too much exposure, and for any range of input grayscales, the output again doesn't change because the output is what we call saturated. So this is saturation level. So in between the saturation level and the fog level is this ascending monotonic curve. And this is where radiography sits at the point of maximum gradient. And some of you can say, I understand why Emmons is saying maximum gradient, because this is the gradient of that curve. And where is this lookup table maximally mapping input grayscales to output grayscales? It's across this range here. Where this graph is steepest, a small range in exposure, transmission or absorption, will produce a large range of image intensity variation. I'm repeating myself because you've seen this 1,000 times. So back on lookup tables, I want you to be able to fill these in. I'm not going to do it for you, but I want you to tell me what these graphs are and how you would use them. You can tell yourself. Should I just skip it and leave it for you to do for homework? Or can you tell me, are you brave enough to click your microphone on and tell me what A does? Are there any brave people out there?
So I think the first one, so if the grayscale is below like certain point, it should be, it should be like completely white. And if the grayscale is above this point, it should be like completely black. So it's a black and white.
So this is binarization.
Yeah.
Right. This turns a grayscale image into either black or white, 2 levels. Okay, brave people, thank you for that. What about B? What do you think B does? So
I think.
Go ahead. Sorry, Brian.
I think, yeah. I think for B, until like a certain point before that, there is a linear response. So, but then afterwards, the entire image appears white.
So no more contrast change from here. This is like saturation.
Yeah.
Okay. And after this point, I've got no contrast sensitivity. Yes? In this range here, there is no contrast sensitivity.
Yeah.
For this part here, from here to there, this graph is quite steep. And so the contrast sensitivity here is quite strong. In other words, if I made this graph steeper still, then the contrast sensitivity over this range would be stronger still. So I'm interested in two things. Where does this graph go up to and how steep it is? But you're right, this is a linear response, but with stretched contrast up to this point, and then it saturates.
So it's like before that point, the signal is being like amplified.
Yes, exactly. Amplified here, saturated here. So who wants to have a go at graph C?
Would it just invert the image so anything with low G would suddenly be whited out and anything that with a high G would be darkened?
Yeah, so it is exactly what you've said. It's grayscale inversion, so it's the negative of the image that you put in. And while you're there, has the image been amplified in its contrast resolution?
No, because the gradient hasn't been stretched.
Absolutely, perfect. Well done. So this is a mapping. Had it gone this way, it would be do nothing, because it just says you are out what you are in, but this says you are out what you are in, but with reverse contrast. Perfect, well done. What about this graph here, this little guy here? Graph D, someone who's had a cup of tea and feels refreshed should say, I recognize that. Come on, you cup of tea people.
I think this one is the log. I think it's a log G value map of the DSA.
I think it is too. This is a log graph. And on this graph, I think there was a question on your test about this. On this graph, where is the grayscale contrast preserved?
So around the shoulder level, it's like
about here somewhere.
Yeah.
The slope has to be 1. So if the slope here was 1, the same as that slope, but facing the other way, then this part of the graph preserves image contrast because what comes in goes out exactly. Over here, what happens to the contrast? The gradient is less than 1. It's like this. It's compressing the contrast.
So like fewer differences between like different grayscales.
Yep. So a difference of grayscale in 3 might become a difference of 1. So a difference of 3 here might be remapped to be just 1 difference on the output. And vice versa here, what will happen down here?
So like the tiny noises will be amplified. Absolutely. And the image will become very noisy.
Okay. So the log graph was powerful because it made increments, multiplicative increments of grayscale equal, but it amplifies the grayscale contrast at low levels, preserves them here, and compresses them up here. So this is a non-linear mapping, dangerous but powerful. Right? We need to be careful whenever we don't have linear changes, because the effect in the dark parts of the image is not the same as the effect in the bright parts of the image. In a linear operation, they are the same. So I'm going to just show some quick pictures that show the importance of the range of grayscale. So I'm going to show some 8-bit images here. 8-bit means 256 grayscales. And so these images are all the same levels, same images displayed now with varying dynamic ranges. So the top left image is 256 grayscales, going across 200 grayscales, 150. There's the same data. All I'm doing is reducing not the spatial resolution, but the contrast resolution. I'm mapping these grayscales to be less well spread out in intensity. If we go down a step, we can go from 128 to 64 to 32 to 16 steps. And I'm hoping at this stage you're thinking, oh my goodness, the image doesn't seem to change very much. In other words, if I just showed you these pictures independently, not side by side, you might think that very little has changed. And what does that tell you? It tells you that the human vision system does not have a great dynamic range in your eye and brain. Something like 160 grayscales is the maximum grayscale that you are able to accommodate without consciously looking for grayscale differences. So as a blank canvas, when you throw an image onto your eye, you don't really care when it gets past 160 grayscales. So going up to 256 grayscales, which is more than twice than what you can probably see, makes very little difference visually. And so some of you are thinking, wow, why am I doing CT? Because in CT, we have 3,000 Hounsfield units from top to bottom, from hair to soft tissue or bone. Why have I got so many grayscale steps? Let's keep going down. So here are the mappings that in fact produce that reduction of grayscales. It will become more clear to you what's going on in the next slide. So here is the picture with 16 grayscales. And this is the lookup table that says all you 16 levels from there to there will be shown in this. So there'll be this grayscale. It's still running from black to white, right? The image range is still the same, but the contrast resolution is being compressed because all of these grays look the same in the output. They're saturated to that level. So now, instead of having 256 steps, I've just got 16 steps. And so there are only 16 levels of grey in this image. So I have suppressed the contrast resolution here by making the contrast, the grayscales, more coarsely quantized. Now, why is that important? Well, spatially, the pixels are quantized in space, right? The pixels are here and then one's next door and there's one next door. So we have quantization in space and we have quantization in grayscale. Both are important, but the dynamic range of an image is particularly important at the visual end of your radiographic practice, because at some stage, some dude is going to look at your image and he's going to see 160 grayscales. It doesn't matter whether you're doing CT, ultrasound, or MRI, he's going to see 160 grayscales unless he puts his focus on and says, whoa, look at the mottled speckle noise here. So this is an important lesson that says we need to temper what we try to portray in an image by just having more pixels, more grayscales. If it's not visibly, discernibly better, we shouldn't be doing it. We can go down to 8 levels, we can go down to 4 levels, things are starting to look a bit ratty. We can go down to 1 level and we have what the answer was before. Here is the lookup table that says all these pixels with these colors will be turned off to black. All these pixels past this point, 128, every pixel which is brighter than 128 will be saturated and drawn as white. Even with 1 bit, 2 levels of grey, a substantial amount of the image information is still retained. And this is why the human vision system doesn't bother to factorize into billions of grayscales, because once you get past 100, we've kind of got as much as we need to do useful things. So the rest of the course is going to be staggered around doing things like this. This is like BSA, isn't it? It's like image A, no contrast. Image B, inject contrast. Image C, I should just see where I injected the contrast. Contrast free, contrast full, subtract, oh, this is where I injected the contrast. So we do these global image operations where we take whole pictures and just numerically operate on the pixels so that this pixel is combined with this pixel to produce a final result at this point here. So C is the result of global arithmetic operations, and we do the same for all the pixels in parallel or sequentially. So we do this for all the pixels one after the other or together as we zip along. So this is global arithmetic. We use global arithmetic with some care, because if you're going to say this pixel is going to be subtracted from this pixel to produce an image of where the contrast was injected, if you've got registration problems in DSA, in angiography, if the patient has breathed in before you do the subtraction, then you're going to have misregistration of the subtraction and the contrast will appear in the wrong spot. So if you're going to do global arithmetic, we need to worry about something called registration that says, does this top corner pixel really belong to this top corner pixel so that when I draw this top corner pixel, it's in the right spot. Registration is not that hard, but it's terribly important to get right. We're going to have chords later on in this course, which I'm hoping you're not dreading already. And we're going to talk about what happens if you map an image to something. So instead of doing global arithmetic on images like PSA subtraction, can we actually map in images to be something completely new and completely different? So this is a poor example, but what I'm hoping to convince you of is here is an image in what we call the spatial domain. This is like X rows, Y columns. Can we map it to another completely different image? And here I'm going to call this the Fourier image or the Fourier domain. And it's not done very brightly, but see this little arrow here? I should highlight this and color it red. I'm going to do it right now. This little arrow, boring as it is really important. It says, if I do this mapping from this domain to this domain, I can go back. This arrow has got two heads. It's like Medusa. It can go forwards and it can go backwards. So you can take an image and map it into something which looks completely different. And when you're done with that, you can map it back and nothing has changed. So this will be very important. I'm going to give you some examples in a minute. In MRI, for example, we start here. In MRI, you put the patient in, you're in this space. And then when you've finished acquiring the data, you're in this space and you can say, oh, here is the patient anatomy. We're actually going to begin here. Similar in CT. So here's an example which I've stuffed into the notes which weren't on the ones on the slide. So it says here is an image, a spatial image, X and Y coordinates. These pixels are in rows and columns. Here is an image that says this is the Fourier transform of that image. So it's a completely different representation of this data. It's complex, so it has a real and imaginary part. It's like a complex number. We can show the same information in a different way. So same image, still Fourier space, but now this is brightness versus phase. And so this information is exactly the same as this. And you can see because this image has got quite inclined bits here, which are running in particular angles, there's a correlation between the angled parts in my image and the bright parts in this transform domain. So if you're a clever bunny, you can look at this image and say, oh, I think that's cameraman, based on the distribution of vertical, horizontal, and angled bits. You can say, I think that's probably cameraman. And if we press the button and do an inverse transform, bing, we get this back with no changes, none at all. So this is going to be very powerful because it's like you've got a new option, a new toolbox to play with that says, we can do operations on this image. We can do things like registration, subtraction, filtering, log mapping, noise reduction, but we can also do stuff here. Here is a whole new playground. And whatever we can do in this domain, we can also do in this domain, but with a very different emphasis of content. So this is wonderful stuff. I think you'll love this. So the second part that we're going to talk about is not global operations, but local operations on image data. And the local operations say, here is this image in image A. Remember, we're doing still global arithmetic on the whole image, image A and image B, but we're going to make image B depend not just on the pink pixel here, but also upon its neighbours. So a local operation says, let's take a patch of image A, a little patch of A, and based on the content of that patch, on the content surrounding this pixel, at the right position, we're going to put a new number where the answer depends upon not only what's here, but what's surrounding the original value in the right place. So now we're doing a local operation, and this is called convolution. And now the result that we get in B depends not only on what was in the middle here, but also what was on neighboring adjacent pixels, and also how we look at those neighboring adjacent pixels. I'll try to explain that in the next slide, excuse me. So you see between slide 35 and 36, the only thing that's changed is the sign of those numbers here. It was -1 here. You'll notice that -1, -1, -1, -1 equals 4. So those of you who are already zooming ahead are thinking, oh, Emmons is saying, I wonder how different this pixel is from its 4 neighbours. So I'm comparing myself to you, myself to you, myself to you, and myself to you. And when I say, how different am I from the 4 of you, I'm just saying, if I was the same, the answer would be 0 here. So this local operation can do things like, I wonder if I am the same or different to my neighbours. And at the moment, this configuration is saying, I wonder if I am different to my neighbours, whereas on slide 36, it says, let's put back an answer which in fact averages me, because now I'm adding everything, and now I'm seeing if I look like my neighbours. How much do I look like my neighbours? So the centre pixel here in the output image is the average of me and my neighbours. This is kind of cool. It says, let's see if I'm the same or different to adjacent regions in my image. We're looking at content. This is cool stuff. You're not going to read that, are you? No. Okay. So I'm going to do some image stuff. Not going to read that either, are you? Oh, wait a minute. Yes, there is something here. This stuff here, some of you are thinking, you know, who on earth is going to worry about this? You can now buy software. So watch out, radiographers and angiography people. You can now buy software which will take 3D pictures of your arterial anatomy, and it will find all these joints where you bifurcate, and it will measure the distance between them and the angles at which they come off. And it will try and predict where you've got things like stenosis or you've got abnormal arterial formation. So based on known anatomy, it finds all these critical points in branch structures. It could be for lungs or it could be for arteries or vein distributions. And the software will track through and say, whoa, it's got something strange happening here. And it just goes through the whole tree faster than you can slice bread. Anyway, so slide 39. Slide 39 is saying, imagine that this is going to be an X-ray taken in projection of this artery. So we're letting X-rays fall down like rain onto this artery. And because we're doing DSA, the answer after subtraction will be 0 here, because we'll subtract the before and after images and we'll get no difference, meaning 0. We'll get 0 over here because before is the same as after, because there's no contrast here, and so we'll get 0 here. But in here, where we inject contrast, before is not the same as after, and so we get these curves, which are non-zero curves. And what I'm drawing here in the pink graph is a plot of the intensity running from outside the artery, across the middle of the artery, and back out the other side of the artery. So out here, I get 0 as expected because there's no contrast material on either side of this projection A. But as I go into the vein where there was contrast, where the vein is thicker, for example, where the dot is, then there is more absorption because the arterial thickness in the direction into the board here, into the plane of the paper, is taller. So the height of this column represents the absorption into the board, into the plane of the paper at that point. So towards the edge of the artery, these columns get shorter and shorter until eventually they disappear. I think we did this in RAD2012I. The reason I'm bringing this up again is because if we draw a graph running across this profile, it will look like this. And if we draw a graph of running across this part of the patient's angiography, we'll see a graph that looks like this. And the difference between these two graphs is that because this artery at this point B has been stenosed, that the area under this graph will come from a smaller pipe than the area under this graph. And so rather than trying to measure the width of the artery from these low points, which are hard to find because they disappear into the noise here, so instead of measuring from there to there, we just add up the area under this graph and we add up the area under this graph and we take their ratio. And then the stenosis is just the area of B divided by the area of A, because the area of B is stenosed, and so the cross-sectional area of the pipe. Oh, we're back on this stuff again. We're back here, right? Where we're looking at what does the graph look like depending on the size of the object that casts the shadow. Yeah, this is where we're going. What's so cool about this is, see here, there are no constants, there are no mu's, there's no t's, there's no per second units or anything. Because this is a ratio, we don't even care what KVP was here. All we care about is, did this area look different to this area? Because if they're different, the area of the pipe must be different. And so the pipe is either the same or it's stenosed. You can see here that I need to be a bit careful about drawing these lines, don't you? Because if I was a sloppy radiographer and I drew a line at B like this, it could actually look the same as A. So if I cut this pipe obliquely, it's going to look like this. Whereas if I cut it perpendicular this way, the graph will have a minimal area. We'll talk about how to find minimal graphs, perpendicular cuts automatically, because this is not easy to do, right? This takes a bit of skill to get this cut to be perpendicular to the stenosed area. And so does it here. On a curved pipe, on a straight pipe, it's easy. On a curved pipe, it's art. You've seen pictures of angiography better than that. Okay, so I'm getting to the point where we're getting more tired and less worried about what's happening next. I'm going to spend some time, not today, maybe in a couple of weeks, talking about the blue dotted line here is what I believe to be my true outline of my anatomy. The green boxes here are pixels that say, when I discretize my image, then this is a pixel that's in anatomy and this is air. Anatomy, air, anatomy, air, anatomy, air. And so if someone asks the question, what is the area of this patient's anatomy? In other words, how big is his kidney? I can just count these squares and get the area of the kidney, but I'm going to be wrong a little bit because some of the kidney is chopped off here or included too much here. And so I'm going to worry about, I wonder how accurately I can measure the area of Immensa's kidneys by counting whole pixels, because this is a part pixel and I'm missing something here and I'm missing something there. More importantly, I'm going to say, I wonder what the boundary of Immensa's kidney looks like. In other words, what does the perimeter look like? The area is not so bad, is it? But when you look at these perimeters, well, you can see that the perimeter is going to be a little bit more tricky. I'll come back to that. hang on to that. This is, again, excitement to come, at least in my view. So this is where we're going. We're going towards measurements in images. This next bit here is very quickly, it's not going to be examinable, but I thought I should put this in here so that we know when we're talking about things, we're on the same boat. And also because some of you, if you're not familiar with Excel, at some stage we're going to have to get to grips with numerically adding, subtracting, and combining pixels with their neighbours, and we're going to do that in the lab exercises. So this will be brief. Hold your hats and we go. We know about binary states. We already learned how to make an image binary by having a lookup table that turns pixels on to black or off to white. So all numbers can be represented in binary format, and this is where we're going to get to now. This is like how many bits make an image? Usually 8, but let's see. When we're representing numbers, binary numbers are black or white. And to be black or white, you either have to have pixels which are 0 or 1. This is why it's called binary, because there are only 2 states. I'm reminding you down the bottom here that when you see a number like 207, there is implicit coding in here. This is not a 2, this is 200. How do I know it's not a 2? Because it's 2 places to the right of the 7, and the 7 here is not anything more than 7 digits. 7 times 10 to the naught. 10 to the naught is 1. So this placement of integers is important because as we go left, the numbers become by 10 important every time you take a step. So 19 is a nice number, but it's really made up of 1 multiplied by 9, 10 multiplied by 1, and nothing, there's no 0 here. Because we suppress, when we get to 0 here, we could write zeros forever in front because there are no thousands, there are no millions, there are no sesquitillions. As soon as we have zeros in the front here, we terminate and we leave this number as 19. We need as many significant figures as there are non-zero digits in the leading term here. But notice the sequence goes left padded. This is boring for some of you, so you can kind of close your eyes and think, yes, I know this. But if these are lights that are on and off, this means binary 7. 1, 4, 1, 2, 1, 1. 4 plus 2 plus 1 makes 7. These are units, these are twice as bright, these are twice as bright again. So instead of up by powers of 10, like we did for 209, in binary digits, we're just going to double the values as we go to the left. Here is 0, lights off. This is the least significant bit. The least significant bit is the finest variation in the grayscale. This is the unit variation. This is like our grayscale contrast limit. It's going to be 1, it's off or on in the last bit. The most significant bit here as well is 0, and the most significant bit is always at the left of the number. So MSB, LSB. It's just jargon, but it matters because the MSB is a coarse quantization of image intensity. The LSB is the fine scale quantization of image intensity. So here is how we write the number 5. 5 is 4 plus 1. So it's 1, 1, no 2s, plus 1, 4. That's easy. Here is 3. 2 plus 1 is 3. As a binary digit. Here is 6 as a binary digit. No units, but 1, 2 and 1, 4 make 6. You can see the utility in computers of having binary digits because this is switch off, switch on, switch on. Right? This is binary states in memory, which are either turned on or off to make numbers. We can add them. 1 plus 2 equals 3. So here's a binary addition example that shows the number 1 plus the number 2 producing the answer 3. We can see what's going to happen. We have things like 2 plus 5 equals 7. 2 plus 5 is equal to 7. 1 plus 1 equals 2. Oh, this is like carrying. Remember how you carry 9 plus 1 equals 10? Put a 0 and carry the 1. This is the same. 1 plus 1 equals 2. How many 1s does 2 have in it? None, but it has 1, 2 in it. So we have carries just the same as we do in decimal arithmetic. So we can add them. 1 plus 3 equals 4. We can subtract them. Why do we need to subtract numbers? Well, because when we do DSA, we're going to get positive and negative numbers. So we do need to be able to subtract them. Here is a way. If you're interested, go through this. This is how you make a negative number. It's called the 2's complement. Not going to be examined. Bits to bytes. So this is back to images. Basically, it says if you have an unsigned image, unsigned means no negative numbers. So an 8-bit image, 1, 2, 3, 4, 5, 6, 7, 8, runs from value 0 when all the bits are off, LSB to MSB. When all the bits are on, LSB to MSB, this is 1, 1, 1, 1, 1, 1, 8 times, and that's the number 255. If you add up all of these numbers, they will sum 128 plus 64 plus 32 plus 4, 8 plus 4 plus 2 plus 1, they add up to 255. If you have signed integers, if you have pluses and minuses, you can only show on an 8-bit image from minus 127 to plus 127, and you're thinking that's only 254, where's the extra bit? It's because we need to have 0 as well. So this is how we encode signed numbers. Jargon. If we have a byte is made out of nibbles. This is a byte, an 8-bit byte. These are 4-bit nibbles, an MSN and an LSN, which is on the next slide. So bytes are subdivided into nibbles. Words are made of compound bytes. So a word might be made of 2, 4, or 8 bytes. Your phone is probably made of 64-bit instructions, which are 8 bytes. So there are 8 of these at a time. Your phone handles strings of 8 times 8, 96 bits at a time. Okay, quickly. Oh, keep hitting the stupid things here. Okay, keep going. Some of you will run across images in hexadecimal form. Hexadecimal form is a way of treating an 8-bit byte in nibbles, so that you look at this bit, you think, oh, that's a 3. And then you want it to do with this bit here because it's an 8 and 4, which is a 12. And then you think, okay, let's have numbers that go not 0 to 10, but 0 to 16. And so when you want to count past 9, we just invent new symbols, A, B, C, D, E, F. So A represents the integer 10, B represents the integer 11, C represents this integer, it's 12, 8 plus 4 here. So you'll sometimes see reference in 8-bit imaging to numbers in hexadecimal mode. It's just dividing them into 4-bit nibbles rather than more long bits as words. You know what a megabyte means, you know what a kilobyte means, you know what a gigabyte means, roughly. Let's keep going. When you represent numbers in the computer for images, for example, when we do logs on the log thing, we do this stuff here and we have decimal points. Oh, we've got to worry about decimal points. And so in the computer divides these into mantissa and exponents. And so it divides them into integers before and after a decimal point. What happens when you have things like pi? They're approximated. In other words, at some stage, the machine says pi is not what it is, it's this. And it's wrong, right? It's wrong because the computer says, I'm only working to 10 bits of arithmetic precision, depending on the word length of the calculator or the computer. If I want to write text on an image, like when you're putting patient names in, they're also binary, and they're binary written in ASCII codes. So in ASCII codes, we just say a number is interpreted as a letter if a little flag goes up and says, what follows next is not a number but is text, then a hexadecimal number will be translated as text, M for Mary. I'm not going to talk about computer layout other than show this diagram here, which is kind of important because it says when you're doing imaging, basically you want to be here. This is graphics memory. So we've got some way of acquiring data. We want to take it from memory, from a CT machine. It's passed into a central processing unit. We deal with it, we calculate it, we put it back on the bus and we look at it on the video monitor. At the heart of this is the central processing unit, and the central processing unit says basically how fast can I go, and it's run by a clock. We can talk about these buses because these buses limit how fast you can take an image from disk, pass it into memory, process it, and then make it appear in the monitor. The last bit that happens here is not so important about buses, but if you're interested in the difference between serial and parallel operation, read that. And then this is the last slide for today at 8:56. Basically, we're going to do things like this last thing here. It says, here is image B. Oh, image B at some pixel I is going to be composed of image A pixels at different spots. A pixel plus its left neighbour and its right neighbour. The pixel before, the current pixel, and the pixel after will be added to produce this image B. We're going to do this till you're sick of it. Maybe that's happened already. Maybe you're sick of it already. I'm going to stop. If someone have some questions, I'm going to be around here for a few minutes after. I'm going to stop recording, first of all. Stop sharing. Stop recording.